So welcome everyone for Cloud Computing and Big Data. Today we have our lecture 7. And this is about deep learning applications in clouds and nicely complements our last lecture 6 in many regards, which was basically the really move from machine learning to deep learning. So let's review a little bit what we had the last time in understanding this move away from shallow learning models or from basically, let's say, simple learning models where we really started from. And we really had in the beginning of the course the perceptual learning model, a linear learning model, which is, let's say, still strong, captures the essence of machine learning, but of course has many limits. It still does the job, as we have seen in the initial part of the courses, where we were thinking about a very binary classification problem, simple, just two classes from these flowers. And we want to understand what happens if you see a new flower. And can we then basically classify this new point that we add over here, which standing for the flower here, into an Iris setosa or Iris virginica? And the decision boundary was a little bit key to it. You remember a little bit how we did this with the perceptual model. And with this, we had also the perceptual learning algorithm, which was alongside with this, flipping essentially the vector up, down, or +1, -1, +1, -1, going through all the data set again and again. And if you, for mathematical convenience, describe this a bit more generally, you still have the inputs, sum them up linearly using weights, and the weights, of course, in red here, were exactly the entities we have learned and flipped along with the PLA algorithm and changed over time until we come to the solution that none of these points in our training set were misclassified, and we use a test set then to see that this is really working, usually. Now, this was a linear learning model, simple, an assumption where also the data was linearly separable, right? If you remember some of the earlier lectures. So this is, of course, not always the case. So we need a little bit more non-linearity in the learning models to understand really how we can work with larger problems. Instead of going directly to much larger problems, we have done in the last lecture, however, a step towards a 10 class classification problem. We use the MNIST data set here, and this will be also coming back in your assignment too. So essentially, instead of having just 2 classes, we have 10 classes, all basically the digits that you see here in handwritten characters, and you want to classify from these pictures, which are small pictures, via a neural network or via, let's say, a learning model, what exact digit that is. And if you remember the last time, we also said this is a very nice supervised learning problem. We have the labels, we can learn from it. And with this, creating a classifier, as we call it, that actually captures the essence of this learning task. And with this, hopefully come up to a very good accuracy in determine whether this picture shows a 0, 6, or 4, as I have here. So we extended this a little bit, doing a multi-output perceptron, saying, okay, we still not have many layers, but we maybe have just, the output into 10 classes. And that's what we call the multi-output perceptron. Not really a very strong learning model, but for the simple task here, still relatively good accuracy. If you think about that, about 90% of the data could be correctly classified. And we did this in 20 learning epochs, which then are separated in so-called batch sizes, which is the amount of times you go over the batch sizes and overall then through the data in terms of reaching epoch by epoch by epoch. And that's, of course, all configuration parameters. We learned also that instead of having the simple sign function that we had in the beginning, like +1, -1, for mathematical convenience of the binary classification, we switched to something much more non-linear, which you see here, and they're different of those existing in the pockets of machine learning engineers that basically can choose from these algorithms that are existing as the activation function, so to speak, and then put that in the learning algorithm. Here you have the rectified linear unit. Some say stronger signals, basically everything which is positive gets another boost in a way, because the negative values have just 0 and the positive values are increasing. So, but also the leaky value is used in the current settings in real production applications. So This is a little bit an application domain problem. It's also a little bit alluding to hyperparameter optimization and the neural architecture search topics we will have later in the course, which also requires enormous computing complexity. Speaking of this computing complexity, what we added also in the last lecture was then the idea, and this brings us then to the real idea of neural networks, hidden layers. You see that a little bit doing then the move from this multi-output perceptron here, still with, let's say, a couple of perceptron here, to different hidden layers where different neurons are. And the idea is not really very different. You just take several one of these neurons and put them together in different layers, fully connected with each other. And then in the next layer, the same idea. And of course, the output remains a little bit the similar. You have still the idea of computing probabilities here between the different classes, doing, for instance, a softmax activation function at the end in order to differentiate between the different classes. But what we learned in terms of computational complexity, this is quickly rising, right? And this is a little bit here what we see and had learned in the last time. So the multi-output perceptron was computationally not very expensive. You have here the connections, basically the amount of connections in red here, standing for these kind of 784 times 10 plus 10, if you remember, are the bias here that we have, for instance, here modeled, and then incorporate is one of the learnable, let's say, weight for mathematical convenience again, but still this needs to be computed. And of course, for this, you sort of need little computing. Now, when we took the hidden layers, we put much more neurons in each of these layers, which is a hyperparameter we will talk about also towards the end of the course again, because there's also, of course, with the computational complexity relies. But here we have seen quickly by adding just 2 hidden layers, you already, significantly increase the learnable parameters, right? So this is all these connections you see have to be learned. So we go iteratively again and again over the data. But of course, you have a much more powerful learning model, which captures so-called something we say a universal classifier almost, or universal learning machine, where when you train enough, you have data enough, you can almost prove that a neural network of that kind can learn almost everything. This is an explosive statement today because we have also seen the rise of deep learning, maybe doing several of these jobs also, let's say, much more powerful or much more easier. Hence, we have done and have seen the move from, then this idea of having this neural networks to deep learning models. And of course, this is a big material, a big pocket of, let's say, techniques which machine learning engineers have. Autoencoders might be one example. Then there are, of course, a huge set of transformer models these days we use in research, or what are cutting edge models. So I provided you in the last time something called the basic convolutional neural network, which is something we come back today actually to clarify some more concepts. And we'll also learn that this blueprint you see here of the CNN we had the last time is a little bit derived from a so-called AlexNet, which was one of the first, so to speak, blueprints of architecture networks that actually do the job of computer vision enormously good. Today, you would rather pick ResNet models, residual networks, and so on. I will also make a case about this in lecture 7. But you have seen by doing so, and then I think we can come to the material of lecture 7, just one final remark, that by getting really to a much more powerful learning model here to the NN2 with 2 hidden layers, we already improved in the accuracy, which is just 4%, but it could mean a lot of money in production applications, right? Netflix, movie, rental, whatever, having an accuracy better for 4% over a whole year of movies watched, and people that buy maybe movies in Amazon Prime and so on could mean a lot of money for the people or for the organization. And we have seen then the next subsequent step where we said, okay, now we have the convolutional neural network with an interesting trick, putting the local neighborhood in. And this is something and concepts I want to come back to today, because we were not talking about weight sharing very much. And I just will highlight some of these techniques again to make then also the deep learning a bit better understandable in this context. However, you have seen, and this is the final point here, that we paid the price for it. So there were much more deeper structures, this feature learning that you hopefully remember from the interactive web page that I encouraged you to look at, we have much more parameters to learn, like 1.2 million, in contrast to 120,000 roughly. Hence, you need lots of computing power to actually do this. And in the assignment, you will also understand that there you're reaching the limits of CPUs. So using convolutional networks on a CPU doesn't really make a lot of fun. And it's also, of course, part of the assignment for you to understand. And I will actually demonstrate some of these things, of course, also with practical lecture 7.1 next Tuesday. So let us come then to deep learning applications in cloud. So a little bit the idea of applications, why we go to the cloud. Hence, we're thinking more and more that we maybe need not just one GPU that is somewhere in a workstation, or that some of you maybe have somewhere in their desktop machine, or even in laptops today. We want to have, let's say, 500 GPUs at the same time for an application. And I will make the case for it. So we will do some let's say, overviews why, of course, applications are then going to the clouds. Hence, the scalability will be a key element. We then will go to several AWS tools, just because we have MS Azure already done in the course, and it's good for the idea, I think, to understand that different cloud vendors have different solutions. And here the AWS SageMaker approach is quite interesting. But I want to also show you a little bit the AMI, the Amazon Machine Images approach, which is based on the idea of virtualization and so on. So we will see a little bit the idea of how to connect these types of AWS services with the demands of cloud applications of doing distributed deep learning, which will be one key term coming again basically here throughout the lecture. So understanding why we go to the cloud computing really, and not just stay on a workstation client. With this, we connect to different pieces we had already. Of course, virtualization was already there, so I don't really spend lots of time doing this. We have already talked about SSH keys, so I will link still to some of this material so that you see all of these lectures built on each other and also connected to each other. But we will then go a bit quicker through this to focus a bit more on the AMIs and then a little bit on the AWS SageMaker and the Studio Lab that you then also use in the assignment. In the second part, then, I wanted just to repeat some of the statements from the first part and also from lecture 6, particularly those where we had not much time in lecture 6 because we just were introducing deep learning. Now, here and there, it's good to understand some concepts like weight sharing, for instance, or again, the idea why we need then the cloud and so many GPUs, because we see a tremendous parameter growth, as I was alluding to in lecture 6 already, especially if you look in, let's say, other deep learning architectures, right? When we think about autoencoders, for instance, and so on. And this is then also a nice, let's say, sneak preview at the end of going towards what we call neural architecture search or AutoML techniques, where you basically derive the ideal idea of a neural network architecture automatically. And of course, automatically means a computer is doing an automation and optimization of this. And in this, of course, you need, again, lots of computing requirements that we'll talk to, and then have a later lecture. And this is the one alluding to earlier, this lecture 13 that we inserted now as a new lecture here, because it becomes more and more important in machine learning and deep learning, because there is where the accuracy is. This is what you want to optimize to achieve lower error rates, better accuracy, and perhaps even savings in compute if you have several AutoML techniques, like, for instance, we will talk about ensembles you see in AutoGluon, for instance. But these are all more advanced topics. And this is now really, again, inserted early, if you remember, so that you can now have time also for assignment 2 in the next couple of weeks, so that at the end of the course, we can actually finish then with the final project that will be also handed out and discussed in the next coming weeks. And after that, we will come back to some conceptual lectures so that you have some time also basically for the assignment 2 to solve. So let's start a little bit by another move from applications. So we had this handwritten character recognition that you will also see in the applications in your assignment. But when you think about more realistic applications here, you can think here of one of the examples we have, for instance, here in our research from one of my PhDs, or basically a postdoc now, Rocco Sedona, having several patches here from a satellite in terms of images. And we want to understand, are there beaches in Is this agriculture? Is this trees, forest areas, and so on? So you want to understand from the patches, what is the scene all about? And these are high resolution images taken by satellite, so lots of big data if you want. And this is something which not anymore fits in one GPU or fits on your desktop computer. Hence, what we usually do then is to see how we can use distributed deep learning. And I show you a little bit what that means here in this graph, that not, of course, using any more one GPU, you basically distribute the load and the batches, and this will be now a key concern in this technique, the overall batches of the data. Remember, this is basically also what we had last time, epochs and batches. Over the batch size, you always have, a training, let's say, step, and then you do this certain times in the batches to reach an epoch, and then you have different epochs. The key message to take away is now that we distribute the batches essentially with all that data that we usually would just compute on one GPU on very different ones, right? Different GPUs. Here's just 4, but you see from the graph already here and the computing time on the left that nothing says that we can just use 4 GPUs. So here in the example where we broke down the time to a couple of minutes really, using one of the supercomputers or cloud processing machines if you want, it doesn't matter, with 24 nodes times 4 times GPUs. So we have here 96 GPUs in parallel used using distributed deep learning. And as I was alluding to earlier, this is not anymore also AlexNet or a smaller convolutional neural network. It is so-called residual network, residual because it has interesting skip connections here, a little bit something we didn't have in the convolutional aspect last time, but has stand the test of time of being quite a very good, let's say, accelerator really of learning. At the end, you see the image comes in as an input like we had already the last time, the blueprint here. If you want several convolutions, it still has the activation functions, pooling ideas, and so on. It just has here and there the skip connections. And as we also said the last time, even if it's a fancy now deep learning algorithm and network architecture, the last bits is a FC, a fully connected one, which then brings us again to the classification scheme of saying it's a beach, it's a tree or forest, it's agriculture, etc. So that should bring you now one level more to the idea that for these kind of problems in real applications, you need to go to the cloud, right? Luckily, some of our researchers have these HPC machines available for zero charge. But if you really are a company that wants to do something in this area, or your public sector organization that maybe need to inform, or let's say on catastrophic events happening. We have now, I think, Florida approaching a hurricane. So you can imagine that there's lots of scenarios running similar elements of trying to understand how the damages will be in Florida when the hurricane is actually reaching several areas. So, but this is of course some application then with some specific purpose, but also in forest trees, you can imagine they want to understand over decades the growth, the potential of trees, the diversification of trees, and so on. There are different application domain problems for which this data can be used and what you want to learn. However, now it sounds so beautiful. And when I tell you, okay, Morris said something in the course that you can parallelize without end, you mean, firstly, you see that's not the case. So we reached here, so to speak, with 96 GPUs already the sweet spot that we couldn't do more, essentially because we didn't have data enough. And there's another limitation that will come back when we, for instance, use 1024 GPUs here. On the left-hand side, you see the validation accuracy. So in one respect, the accuracy is all that is quite high in the beginning, given, let's say, the batch size is kept, let's say, relatively small. But as soon as you're starting with increasing the batch size, and you have to increase the batch size when you want to use lots of GPUs. Otherwise, when you don't do this from a global batch size perspective, you have the GPUs that have nothing to work on, right? You have, or just let's say, minimal data to work on. Hence, only for large batch sizes you want to do this in a way. But we see also then by doing the large batch sizes, you have the drawback that the validation accuracy quickly drops. And this is something which is depending on different learning rates here in a more drastic manner or not. So these have been studies by Marcel, one of my PhD students here. For instance, where I show you with this regard, there are limits in parallelization. You cannot use a cloud infinitely if you want, of saying just I want 4,000 GPUs, 10,000 GPUs, and I can learn every problem I want. So this is known as a problem of large batch sizes, and everybody has this. We were discussing it at the supercomputing conference, even with Facebook, right, and other big players in the domain. So this is a common learning problem if you want. But it captures nicely now the essence and connecting to some of the lectures we had before. So of course, you know the Google Collaboratory by now. We were having this a couple of times already in our course, where you can pick one GPU or TPU. It's equivalent to the idea of having somewhere under your desktop or under your, let's say, laptop regime, some GPU and one. In one respect, this is not anymore working, right? Hence, you can go to Amazon Web Services, needless to say, the Google Cloud, or essentially also the MS Azure platform will have similar services. And this is really then the motivation that we just have seen in the application. We have lots of big data where your little computer is not anymore working. And when you then combine it with some medium deep learning networks that we have seen, maybe just the ResNet 50 could be considered as a medium deep learning network. Maybe autoencoders and large transformer models these days are rather the large deep learning networks. For this, you really need to go to some cloud computing facility. And of course, when you are having, let's say, also science in the back, then there's a chance of getting Euro HPC resources we discussed earlier in the course, where you don't have to pay. But in the industrial world, where the most of you maybe will be living in after studying and basically graduating, this will be your case of going then to the cloud for larger, bigger problems. Now let's see how that reflects now when we want to use AWS for something like this, what changes we have to do. Also think about that the distributed nature of this means I maybe don't really need the Jupyter notebook in front of me, right? As particularly in the light of the fact that some of these trainings maybe take several hours, right? When I don't have maybe 96 GPUs, I'm still maybe in the regime of some hours or so to learn from this. Hence, I need something which is a bit more batch oriented. So where you submit your job, where you work with some, let's say, virtualized deep learning EC2 instance. And here, of course, now is something what we already learned, that EC2 gives us the opportunity leveraging virtualization and have a certain instance of this virtualization instance somewhere in the cloud, connecting nicely to the storage S3 services we have also seen in previous lectures. And I can use an SSH client with the SSH key in Azure to connect to it. So far, so good. We know how that works. We had done the key pair generation, but now comes a distinct difference. And this is something, again, relating to what we learned in Spark a little bit, that, of course, having the whole ecosystem of Spark, if you remember, with Hadoop, the right versions and so on, all together working, means quite a lot of work for those that have to configure and install and administrate it. Hence, here the Amazon Elastic Compute Cloud gives you something they call AMIs. This AMIs are machine images, which basically are directly alluding what we had to lecture 4. So virtual machine instances that you can use based on existing catalogs and templates where already some, let's say, deep learning tool sets that we want to use in this are already installed. So when we go to the AWS Elastic Compute Cloud, for instance, here, and I will demonstrate this in practical lecture 7.1, hence here and there I go a bit quicker because in one respect, it also is showing you some practical aspects. This is how you would do it now when you think about distributed deep learning. You would go to the cloud, you will take the AWS AMI images in the Amazon EC2, and you would pick particularly those that are on deep learning. However, if you do this, take away the message that you want probably those with GPU acceleration. So you will see a large set of accelerated computing instance types, right? So it's not really fruitful for us to have now an AWS image from deep learning AMIs on a CPU resource where then deep learning will be terribly slow, right? So hence you would combine this in a smart way using the instance type of accelerated computing. There are also lots of descriptions online for these different instances that Amazon provides. And you can see as a P3 example here, these are, for instance, NVIDIA V100. V stands for Volta architecture of tensor cores, V100 cards available. So with this, you can really do quite decent deep learning. And given you have then a couple of Amazon EC2s you can connect to each other, you can then start also going the distributed fashion, so using even more than 8. To do so, and again, I will demonstrate it a little bit, you have to pick wisely what of these deep learning frameworks you want to use in this different Amazon images that you can select here. You see here, for instance, PyTorch was one package we discussed. TensorFlow, including also Keras, was another one we discussed. The beauty here is everything is perfectly configured already with all the necessary NVIDIA drivers, CUDA versions, Nickel. So all the underlying, let's say, library parts that are required to really use TensorFlow in at good speed. And I just wanted to give you also a sort of new impact here. And I know the cloud computing is a little bit on a higher level than our high performance computing course. Just take away the message that the idea of doing CPUs these days is also a little bit different than just the normal x86 processor units you probably know from Intel, and that have been quite known in the past. There are also newer versions of so-called ARM architectures, which are a little bit more lean. This is here a little bit by this idea of the reduced instruction set idea, and that is less computed per cycle, making them, or these processors, a little bit more cheaper in a way. In some respect, let's say the last years, it was also thinking about more mobile devices that should have ARM solutions, while others maybe still carry the x86. But we see also now in supercomputing and in larger installations of computing, even ARM processors. Here's an overview. What is basically now the idea? Energy efficiency goes with it, but the reduced instruction set. And it's just another type of resource. I mentioned this because you see that you have to pick that for which basically you want to have this image. This is related to the virtualization part in this respect from the Amazon machine images. So a little bit of dive down. I know for the cloud computing course, still a little bit of stretch. So we pick one of these instances, and the default instance you see here is a T2 Micro, for instance, which is not really very powerful. Hence, when you want to do real business on real GPUs, you have to go the P3 way. In order to save costs, and because it's just a demo here, and also next Tuesday, we pick, let's say, more moderate resources here every now and then, because you can imagine as soon as you pick even with these images, underlying compute needs to be paid, and additional costs apply, of course, of having this pre-installed software with the AMIs, because you don't have to install TensorFlow anymore, PyTorch anymore, and all the necessary drivers you see here, essentially with PyTorch and so on. This is very neat and it saves you a lot of time when you want to really do this. And by having this instance then started, it basically is a little bit seen here. It will be launched. You have to wait a little bit. You will have to configure this key I was pointing to before, so that you have an SSH key in order to connect exactly to this, let's say, AMI image that is now an instance that has been launched, basically based on the template that you had using the virtualization underneath. And then you can connect to the instance, and I will demonstrate this also on Tuesday. You see also the hint here, there are some other solutions, Amazon SageMaker, right? So you see Amazon is smart. For a fully managed experience, please use the Amazon SageMaker. And this is another tool, but this is a much more low-level tool where you now have, let's say, the operating system and all the tool sets ready. And now you can start coding in Python and executing, or you use even distributed deep learning that we will also learn a little bit later. Again, the point is review costs, of course, in one respect, but of course, think about that deep learning is really effectively only with GPUs. And in this regard, the T2 Micro that is in the free tier really doesn't give you a lot of computing in that regard. So coming then to the idea of another service. So this was quite low level. You have to still, let's say, do your commands on a command line interface. We want to see, is there not something interesting that is a little bit like MS Azure, right? Where we had the HD Insight and we had a nice Jupyter Lab on it and a Jupyter Notebook. And this is the Amazon SageMaker services. There are different, let's say, flavors of it. You will learn something about a SageMaker Lab. That is basically part of your assignment, which is a little bit, let's say, streamlined for mass use, almost like the collaborative, the Colab, basically, from Google. And I will also come back to the service again throughout this course, also when we think about lecture 10, for instance, the software as a service solution, but also later then, again, with parameter optimization, when you think about the tuning step. So you build your models, you train them again in Jupyter. That's what we want, but this time not in MS Azure. We put it in Amazon, computing clouds. But this is a little bit, let's say now, a very similar procedure, right? So you would have the SageMaker or the Studio Lab, and I will again demonstrate this, of course, in our next lecture, a little bit more on the practical perspective. You can then, of course, think which of the compute infrastructure elements you want to use. There's specific ones optimized for machine learning, for instance, here. And of course, there goes also the cost again, depending on the powerful, let's say, resources you will pick. And it's a similar procedure. And then you have Jupyter Lab and many different possibilities to use that. Again, machine learning like we have almost used in the Elastic MapReduce or in MS Azure with Spark. Now you basically can do lots of different elements also in the cloud. And the interesting thing is that this is then also possible to connect with distributed training. This is something which is then needed if you really want to use the 1,000 GPUs that I said in the beginning, when you have a real life problem, not anymore this character recognition. We have, of course, a notebook access, which is quite nice. And you can even put SageMaker on an Elastic MapReduce cluster. So you see quite some flexibility on the back end, as we call, which then gives us, again, the scalability also in order to make training then, let's say, faster. And this automatic model tuning then, of course, will come back to us in later lectures, as I said, the best parameters and hyperparameters. But the point here is, of course, that you have to think we do two things with this computing. Firstly, with distributed training, we accelerate the training. We make a speed up. It's faster. But with the automatic model tuning that also computational resources enable, you get better models. So with a combination, you train better models faster, right? So if you go to your boss in the company and you want to convince him, hey, cloud computing is a good solution for machine learning, and he says, why? Then you would say in many cases, maybe not in all, in many cases, distributed training combined with automatic model tuning means basically your AI models are trained faster and you have the better model in the end. It's the same, let's say, slogan we do with all the SMEs here at the National Competence Center in Iceland, and try it out with many different industry collaborators. And also in science, we have remarkable results working, for instance, with CERN in hyperparameter optimization. So an interesting topic. Much of this is now sort of, I think, better understandable when we would move to practical lecture 7.1, where I will show you basically in a live demonstration, as usual, how that all works together. Here you can see it's all quite neat. You go to Amazon SageMaker in your service portfolios on the AWS dashboard. Then you create a notebook instance. What you have to do is shortly to give the right permissions. This is relating to what we also had earlier, so that others can use your Elastic MapReduce cluster, for instance, or that others can also use your SageMaker notebook here. So you can actually configure a lot of these roles there. Here's a standard role that we use. We have to name the notebook. It takes some time. So when you basically create this, it's around a couple of minutes where it's in the pending mode. So it's not a really direct one-click thing. But once it is in service, you can open Jupyter or open Jupyter Lab. Also, the difference between the two, I want to show you much better, I think, in practical lecture 7.1. And then you can use the Jupyter notebooks, as you know, really already with Spark. in this course, right? We have started with this a lot, but we move away a little bit from Spark now because we want to do something else. We want to do machine learning on steroids using deep learning tools like Keras, for instance, here. Keras these days is also part of the TensorFlow distribution, another deep learning tool. And what you see here is essentially reflecting directly your assignment 2. And I will also demonstrate how you will work with this Jupyter Notebook areas also in the different lab areas I was alluding to. So this is all coming in the next lecture. And with this, we have already basically concluded the first part of the lecture now. I just wanted to play a little bit of video here. And of course, feel free to get some, drink or so in between. And then we start after 10 minutes again. I will just stop the video here.